Hello. In this short podcast, we're going to be working with the binomial distribution. And you may have come across the binomial distribution before. It's a very important distribution in probability and is used a lot in statistical modelling. So I'm going to take you through some of the main ideas behind the binomial distribution, and we're going to do this using an example. And we're going to start by imagining that we have three independent patients. And by this I mean that the characteristics of one patient do not affect the characteristics of the other patients. And in this scenario, each patient is given a medical drug. And the aim of the drug is to reduce blood pressure. So what we actually have here is we have a test or a trial, and the test has two outcomes. And the outcomes can be that the blood pressure is reduced, and this is thought of in general as being a success, and we're going to denote this with the capital letter S. Alternatively, the blood pressure may not be reduced. And we're going to think of this in general as a failure, and we're going to denote this with the letter F. And this is why we're talking about a binomial distribution. It's binomial because it's bi, meaning two, and nomial meaning name. So there's two possible outcomes, success or failure. So we have two outcomes. And that's why we've got the binomial distribution. Now, we're going to further assume that it's known from medical data that the probability that we have a success, in other words, the probability that the drug reduces blood pressure, is 0.3, and we're going to use the general notation P for the probability of success. That this means that the probability of failure is 0.7. That's because the outcome can be either a success or a failure, so those two must sum to 1. And in general, we're going to denote the probability of failure by Q, which is going to be written, which equals 1 minus P. So we introduce some notation. We've got S for success, F for failure, P is the probability of success, and Q is the probability of failure. And what we're going to be interested in this example where we have three independent patients, we're going to be interested in answering questions such as, what is the probability that the blood pressure is reduced in exactly two of the three patients? Now, this can be written as the probability that we have exactly two successes out of three. And we could also write that as the probability that x equals 2, where x is the number of successes. So what we're going to do now on the next page is we're going to find the probability x equals 2, the probability there are 2 successes out of 3. So let's begin by just writing out what we're trying to work out. We're trying to work out the probability x equals 2. And as we've just said, that's the probability of 2 successes out of 3. So just let's think about how 2 successes out of 3 could occur. Well, they could occur as follows. The first patient is success, has a reduction in blood pressure. The second patient is a success, and the third patient is a failure. Or we could have SFS or FSS. So in the last case, the first patient doesn't have a reduction in blood pressure, while the second and third do. So this event of 2 successes, exactly 2 successes out of 3, occurs in 3 possible ways. And then we can look at the probability of each of those individual events. So we could ask ourselves, what is the probability of S, S, F? Now, we have 3 patients and they're independent. So because they're independent, we can multiply probabilities. So that's the probability of S times by the probability of S times by the probability of F. And that's equal to 0.3 times 0.3 times 0.7, which is equal to 0.3 squared times 0.7. So the probability of the first event above, SSF, is 0.3 squared times 0.7. And if we look at the other 2 events, they both comprise 2 successes and a failure in different orders, but that doesn't matter. When we work out the probability in the way that we've just done, we get the same answer, 0.3 squared times 0.7. So the probability that we have SFS is the same, 0.3 squared times 0.7, and similarly the probability that we have FSS is again 0.3 squared times 0.7. And this means that overall, if we're interested in the probability that we have exactly 2 successes out of 3 trials, that's just 3, because there are 3 possible ways that we can have 2 successes and a failure, multiplied by 0.3 squared times 0.7. So another way to think about that is what I'm doing is I'm adding up these 3 probabilities here, 1, 2, 3, corresponding to the 3 possible outcomes, 1, 2, 3. And therefore, that gives us the probability that we have exactly 2 successes out of 3. Now, this number here, 3, is the number of ways that 2 places for S can be chosen. So what do I mean by that? Well, in the first case, the 2 places for S are SS, the first 2, followed by an F. So if we look at the first one here, we've got first and second S's. And then we have the first and the third place is occupied by S. And here we have the second and third places occupied by S. So that's the 3 different ways we can choose the 2 slots out of the 3 where we're going to put the s. And in general, we use a different notation here. We can say 3 choose 2 is the number of ways of selecting 2 objects from 3, or we sometimes write, and this is what I'll be writing later, 3, 2 as a bracket, the number of ways of choosing 2 out of 3. So what we're going to do now on the next page is we're going to study this choose notation in a bit more detail. So we're now going to think about how to choose, in general, x objects out of n. And in general, we're going to write the number of ways of choosing x objects out of n as n and x in a bracket like that, or n choose x. And I prefer the first version here. Now it can be shown that the number of ways of choosing x objects out of n is n factorial divided by x factorial times n minus x factorial. We aren't going to discuss this result in detail today, but you might like to think about this in the light of what we see later. So what does this factorial mean? What is n factorial? Well, n factorial means we take n and then we multiply that by n minus 1, by n minus 2, and so on, all the way down to 1. So n factorial is the product of all the numbers up to n. So as an example, 3 factorial would be 3 times 2 times 1, which is 6. And then a more complicated example, 4 factorial would be 4 times 3 times 2 times 1, which is 24. And then perhaps a less complicated example, 2 factorial is 2 times 1, which is 2. 1 factorial is just 1 on its own, which is 1. And then for notational reasons, 0 factorial is defined to be 1. So let's apply this to what we've seen before. We were asking ourselves, what's the number of ways of choosing 2 objects from 3, 2 slots for the S when we have 3 possible slots? Well, by the formula above, that's 3 factorial divided by 2 factorial times 1 factorial. So note, please, that the 2 numbers on the bottom, 2 and 1, if they were taken separately, they would sum to 3, the number at the top. So let's now expand that from what we know. 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. And then we have the 1 factorial on the bottom. So this is 6 over 2 times 1, which is 3. And that's exactly what we saw above. So this has confirmed the result that we saw above. Now let's have another example, and I'll move on to the next page for this, as we need some space. If we wanted to work out 4 choose 2, the number of ways of choosing 2 objects from 4, then by the formula, that's 4 factorial divided by 2 factorial times by 4 minus 2 factorial, or 4 factorial divided by 2 factorial, which is equal to 4 times 3 times 2 times 1 divided by 2 times 1 times by 2 times 1. So a lot of multiplication, but there's also some simplification. This simplifies away with this, and that gives us in the top 12 and on the bottom 2, and that gives us 6. So from that we know that there are 6 ways of choosing 2 objects from 4. And I'll just quickly, if I can, write down those 6 ways. We have SS, FS, SF, 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 FS, FSSF, FSFS, and FFSS. So the first lot start with an S, and the other lot start with a F. So there is another example of the use of the choose notation. So now we're armed with that, we can go back and start again talking about probabilities. So now let's ask ourselves the question we were asking before. What's the probability that we have exactly 2 successes, S out of 3? And now we could write that as 3 choose 2, the number of ways of choosing the places for the 2 successes out of 3, multiplied by 0.3 probability of success squared, multiplied by 0.7 the probability of failure. And as mathematicians always like to do, we can generalize this. And the way we think about the generalization is we'd have n independent trials each trial can have an outcome, and it can have 2 outcomes, either a success or a failure, and that's why we're working with a binomial. And we also know that the probability of success is a p, and the probability of failure is q, which has to be 1 minus p. Then the binomial distribution tells us that the probability we get exactly x successes out of n, and that could be just written more succinctly by saying probability x equals little x, then that probability is given as n choose x, so the number of ways of choosing the places for the x successes, p to the x, so you've got x independent successes, each of which has probability p, q, n minus x, so the remaining n minus x have to be failures, which takes place with probability q. So note here that if you took these indices and sum them, they sum to n. Now, if you like statistical computing packages, there's one called R, and in R you could work out this probability by using the function d binom, and you'd write d binom x n p. So that would be the way you'd write it in R. In mathematics, we'd write x follows a binomial distribution with parameters n and p, where n is the number of trials and this would usually be fixed by the design of the experiment, and where p is the probability of success. So that would be a mathematical shorthand for saying the random variable x follows the binomial distribution with number of trials n and probability of success p. Let's see a quick example of this. So we're now going to see a bigger example than we've seen before, we have 5 independent patients and we want to know for those patients what's the probability that blood pressure is reduced in exactly 2 of those patients. Well, in this case we would just identify that we have n equals 5 trials. We have that the random variable x, which is the number of those that result in success, follows a binomial distribution with parameters n equals 5 and probability of success is 0.3 as before. And then we can work out the probability x equals 2. The general formula is n choose x, p to the x, q to the n minus x. That is, in this case, 5 choose 2, 0.3 squared, so you've got 2 successes, 0.73, 3 failures, and that can be now worked out as 5 factorial divided by 2 factorial, 3 factorial, 0.3 squared, 0.7 cubed, and if we expand that, we get 5 times 4 times 3 times 2 times 1 for the 5 factorial, divided by 2 times 1 times by 3 times 2 times 1 for the 2 factorial and the 3 factorial. Then we've still got the 0.3 squared and the 0.7 cubed. We can then do some simplification. The 3 times 2 times 1 can be removed. So that's equal to 20 over 2 times 0.3 squared times 0.7 cubed, which is equal to 10 times 0.3 squared, 0.3 squared times 0.7 cubed. And if we work that out on a calculator or by using R, that's 0.3087 if I've done it correctly. So that's the probability you'd see exactly 2 patients with reduced blood pressure when you look at 5 patients, and the probability the drug reduces the blood pressure is 0.3. Now we're going to see a more complicated calculation. We're now going to ask ourselves, what's the probability that the blood pressure is reduced in 0, 1 or 2 patients out of the 5. This is mathematically the probability that x is less than or equal to 2. And that's referred to as a cumulative distribution function. And I'll say a little bit more about that in a second. We could work out that probability just by working out the probability x equals 0, so that's no patients have reduced blood pressure, plus the probability x equals 1, that's 1 patient with reduced blood pressure, plus the probability x equals 2, that's exactly 2 patients with reduced blood pressure. So in a sense we're accumulating the probabilities, and that's why it's called the cumulative distribution function. If we now write down those calculations, that's 5 choose 0, 0.3 to the 0, 0.7 to the 5, plus 5 choose 1, 0.31, which you've got 1 success, 0.7 to the 4, plus 5 choose 2, 0.3 squared, 0.7 to the 3. So one of the reasons why we looked at this example is that we can see there's a pattern 0, 1, 2 and 5, 4, 3. So we've got a pattern going on there. We can see also we've got a 0, 1 and a 2 in the bottom of that bracket. And I'm not going to write out the details of all those. You can check them for yourselves. If I've got that right, that gives you 0.83692. So that could be just done on a calculator. If you wanted to work out a cumulative probability distribution in R, you could do that by using P binom. And in this case, you'd say P binom 250.3. So that's the end of the basic introduction to the binomial distribution. We've seen how to work out some probabilities. We've seen various definitions. I want to finish with some more advanced material, and I'm going to talk about what are called moments, and I'm going to talk about estimation. So, as I said, this is advanced material, but if we have that X follows a binomial distribution with parameters n and p, then we could ask ourselves, what do we expect x to be? So what do we mean by that? Well, can we have a one-number summary that expresses all the information in that random variable, which tells us what, in a sort of average way, we'd expect that random variable to be? And that's called the expected value of x, sometimes called the mean of x. And it can be shown by some mathematics that if you're adventurous, you could try that that's equal to n times p. So that what we expect the random variable x to be would be n times p. And as a simple example of that, if you have x following a binomial distribution with n equals 5 and p equals 0.3, then the expected value of x would be n times p, which is 5 times 0.3, which is 1.5. So on average, we'd expect that random variable to take the value 1.5. Of course, it never takes the value 1.5, but the average of all possible values in the long run that that random variable could take would be 1.5. Similarly, the variance of x, which is a measure of spread of x, can be shown to be n times p times q, where please remember that q is 1 minus p. And if we now work that out in the example, then the variance of a binomial random variable following n equals 5 and p equals 3 would be n times p times q, which equals 5 times 0.3 times 0.7, and that's 1.05. So that's a measure of the spread of the random variable. So sometimes the random variable takes the value 0, sometimes it takes the value 1, sometimes it takes the value 2, sometimes 3, 4, and 5, and it takes those values with certain probabilities that we've seen already. Well, on average, you'd get 1.5, and a measure of how spread out those 0, 1, 2, 3, 4, 5 values are would be 1.05. So that's one advanced point, and expected value of x and variance of x are moments of that random variable. As another advanced topic, but a very useful one, it's very often the case that we have to estimate the parameter p. So p is the probability of success. We have to estimate that from data. And this is very easy to do, because let's say that you find that out of 5 patients, have reduced blood pressure. So we could then recognise that we have n equals 5 and we have x equals 2, and then we'd estimate the probability of success if we didn't know it. We'd estimate it as x over n, so the proportion of successes, which in this particular case of this example will be 2 over 5, which is 0.4. So we can estimate the probability p to use in the equation from data, and that's a very useful thing to do, and that's what very often happens in practice. In the example we were looking at, we took the value p to be 0.3, but where does that value 0.3 come from? In general, it would come from a scientific experiment in which you'd count up the number of successes in a particular number of trials, and then p would be estimated as the proportion of successes, x over n. So I'm going to stop there. I hope that you found this session useful, and what I aim to do today is to introduce the binomial distribution. We've performed some calculations with it. We've met the n choose x notation, which is a very useful notation. And then as advanced material for this session, we've looked at or worked with the expected value and the variance of a binomial random variable. And we've also estimated the probability of success p from data. So thank you very much for your attention.